So for the purpose of this video, it's going to help that you understand the standard color codes that are used for all model kits. Black is always going to represent our carbon atom. White will always represent a hydrogen atom. The red is going to be oxygen. The blue is nitrogen. Yellow is sulfur. And the purple lavender color at the bottom tends to represent phosphorus. There's other atoms, atom colors that we'll use occasionally here and there, and when we do, I'll introduce those, like bromine, kind of be like a dark greenish blue or something like that, or dark green, usually a dark green. These are the standard ones that we're going to be using in modeling, what we're going to be doing this semester. So with that, let's jump into the video and let's put some of these together and let's figure out what our bonding patterns look like for some of these molecular compounds. Hey class, welcome back. So this video we want to take a look at what are called Lewis structures, and from your earlier studies in chemistry, I need my coffee, excuse me. From your earlier studies in chemistry, we know Lewis structures are a way for us to represent what's happening with an atom or a group of atoms that might be bonded together in some pattern, and we're looking at valence electrons. So just the electrons that are on the outer orbital of a single atom or groups of atoms that we would call some sort of like a molecule. We'd call it a molecule. And so for this purpose of this video and these lessons here, particularly, we're going to be looking at bonding patterns with molecular compounds, which means we're working with covalent bonds. So remember, covalent means co, together, valent, we're talking about the valence orbitals, so the valence electrons. So covalent, those electrons are being shared back and forth. So that's what covalent means, kind of that sharing, right? So with that said, let's jump in and take a look. Let's take a look at a couple of things here. So water. Water, we know H2O. I'm gonna go back to, I'll use red for something else. So let's just, let me hold on my pencil. So I like yellow. No, I'll go with white. All right, so we've got H2O. There are three simple rules to whether or not we're dealing with water or dealing with any other molecule, and that is this. Number one, you want to get the sum of the valence electrons. You want to add up all the valence electrons that are there in the molecule. That's the first rule. So right here we see hydrogen. There's two hydrogens and there's one oxygen. We remember from previous studies that hydrogen has one valence electron and oxygen has 6 valence electrons. If you forget how to determine that, you're going to want to go back and watch the lessons I had in basic atomic structure where we figured that out. 2 times 1, 2 valence electrons. 6 times 1, 6 valence electrons. So we're going to need 8 valence electrons altogether. Rule 1, done. Rule 2. Next, we just want to bond all atoms together. Okay? Bond all atoms. We're gonna just bond them together. We're going to use bonding pairs. So each time we draw a line between 2 atoms, that's going to represent one bonding pair, which would be obviously 2 electrons. So you should also remember hydrogen, one valence orbital, one orbital period, valence or regular, and it only has that one electron in that outer orbital. So that means hydrogen will never be at the center of any molecule, and it tends to literally just bond to the outside, to the empty region, so to speak, or to regions that it can very quickly, easily share its one electron with something else that has just a single electron space available, right? So that means in this molecule, water, dinitrogen monoxide, that the oxygen is going to have to be at the center of the molecule. So that means we would have to put oxygen and we would have to bond the 2 hydrogens there, right? Rule 2 is done. Rule 3. At this point, we're going back to the octet rule. So we need to satisfy the octet rule. And so you should remember that that's the rule of 8, right? That's the rule of 8. So we can have no more than 8 valence electrons around any one atom anywhere on the molecule. The exception is hydrogen. It's a duet rule. That's 2, right? So at this point, we have, this bonding pair and this bonding pair, that's a total of 4 valence electrons, or that's 4 valence electrons that are bonding together, right? So we needed 8, so we only need 4 more electrons, all right? So as a result of that, then if 4 more electrons, that would be 2 pairs, because 2 times 2 is 4. So we would put a lone pair here, and we put a lone pair here. And so you want to satisfy the octet rule by adding lone pairs. So lone means alone, and they're paired up together. Hang on. The video, the light came back on. So lone pairs. So there's a pair there. Lone means they're not bonded between 2 atoms. The only time you draw a bonding pair, a bonding line, is if between 2 atoms, obviously. Otherwise, there's nothing to bond to. So now we go back and we check rule 1, 2, and 3. Make sure all 3 rules are satisfied. If they are, then we can trust that this is a proper structure, all right? So rule 1, sum the valence electrons. Do we have 8 electrons total? Well, there's 2 here, 2 here, 2 here, and 2 here. That's a total of 8 electrons. Check. Rule 1 is good, all right? Let me back all this up. So rule 1 is good to go. Bond all atoms. All the atoms are bonded. Satisfy the octet rule. So around hydrogen, there should only be 2. And remember, these are covalent bonds, right? So they're sharing electrons. So there's 2 around there, 2 around there. So hydrogen is satisfied. The duet rule. Oxygen should have 8. And there are 8. So there's 2, 4, 6, 8. So it just so happens that all 8 that we counted for the entire molecule are also centrally located around the oxygen atom, which is at the center of the molecule as well. So we can say that we have satisfied that. When all 3 of these rules you are satisfied, then the molecule, it's good to go. If any one of them is not properly satisfied, if by adding in lone pairs for rule 3, you suddenly have more electrons or less electrons than you need from rule 1, the whole thing is wrong. It's not even partially correct. The whole thing is wrong. So with that said, let's take a look at this. So we've got oxygen at the center, right? Remember, oxygen, it's red. So what we need is, we need a way to bond this. And according to this structure here, we see that there's 2 bonding pairs. So there are these little structures here, just a little line. We're going to represent with a line. But on this oxygen, there are 2 holes that are available. So I'm going to sit here. I'm going to add 1 bonding pair here and 1 bonding pair here, because the oxygen is bonded to 1 hydrogen here, and we can see, right? We can clearly see that right here I went oxygen, and it's bonded to this hydrogen on that side right there, okay? And then we can see that we have another hydrogen. So I'm going from this hydrogen to that oxygen. And so now you should be able to clearly see I went from the oxygen to that hydrogen right there. And this right here represents the shape of this. So now we draw this. There's the oxygen bonded to a hydrogen at this angle. We'll talk about angles and stuff in a later lesson. let me go turn that light back on. The question is where are the lone pairs? Remember, there's a lone pair here and a lone pair here. So there's two lone pairs. But on this modeling kit, you don't see lone pairs. They have to be somewhere. Okay, so for that, I'm going to go to a different modeling kit to help represent this. Okay. Red is still oxygen. Okay. And then white is still going to be hydrogen. And then so if you look here, it's a small little white piece. It's just a different kit. This kit is useful for this reason right here. So you can see here on this piece that I'm holding one post, and then you see there's 4 other posts. 1, 2, 3 posts, okay? So these things are arranged this way, not because we wanted to make the kit useful, but because through many years of experimentation and validating those results, we have figured out, we being the science community, has figured out that this is basically what tends to happen under normal conditions. Normal is a very relative term when we're talking about molecules and atoms and stuff like that. However, these rules tend to be supported, they are supported with data. So we have oxygen bonded to a hydrogen. You can see that I put oxygen bonded to a hydrogen. And on our water molecule, right, what we have to do is now bond this one right here that I'm holding. So I'm going to take another bond and another hydrogen and bond them together. So you should be able to see this is the one we started with, and they're both the same shape. Okay, so now the question is, on this one, we already know, looking at our molecule, that there are 2 lone pairs that need to be here somewhere. What this kit right here does is it helps us visualize where those lone pairs still are. So this empty post on this represents the space where there is a pair of electrons. So there's a lone pair right here, and there's a lone pair right there on that region of space right there. Now on this particular kit, it's not there, but you have to, in your mind's eye, be able to visualize this, all right? So what we do know is, you see how they come out at these angles. So what we do know is that there's a lone pair here and here. They are at those angles, okay? They are at those angles. So now this represents our Lewis structure for water, all right? This represents our Lewis structure for water. So this right here is the basic Lewis structure that satisfies rule 1, 2, and 3. This one right here satisfies the actual molecular geometry, the shape of the molecule itself. What you have to be able to do is, in your mind's eye, know that around this atom here, the octet rule, 2, 4, and then there's 6, 8. There's 2 lone pairs. There's the other 4 electrons. You just have to be able to visualize that in your mind's eye. Okay. Let's go practice another molecule. So let's take a look at a second structure. Let's look at one that you're familiar with, carbon dioxide, right? So we all know carbon dioxide, CO2, right? All right, let me go ahead and put that, be consistent. I'll put that in white, just so I can try to be as consistent as possible. That looks like cobalt. Okay, carbon dioxide, right? We've known this forever. That's the molecular naming system for that. 1 carbon, 2 oxygens, all bonded together. What does this molecule look like? We can use Lewis structures to help us determine the 3-dimensional form of this thing, the molecular geometry, the shape of the molecule, all right? So rule 1, we're going to sum all the electrons. So we've got carbon and we've got oxygen, right? So we see 1 carbon, 2 oxygens. And we know from previously that, from the previous example, oxygen has 6 valence electrons, and we've learned previously in the past, go back, you can look at a periodic table, you know that there's 4 valence electrons. So that's 4 valence electrons that carbon is bringing to this molecule, right? Valence electrons to share in covalent bonding patterns in some way. And then there's 12 electrons from oxygen. And so we need a total of 16 electrons. When we have a total of 16 electrons and we've satisfied all 3 of these rules, then we have a proper Lewis structure. So let's jump in. Let's see what we can do from here. So rule 1, so far we've accomplished rule 1. We'll see how this works. You always go back, just like on the previous one, you check. So now bond all the atoms. Carbon will always be at the center of a molecule. If carbon is present, for every example that we're going to do, carbon will always be at the center, and that's pretty much the case all around. That's one of the dynamic aspects of carbon. Is you'll remember from what you learned in earlier chemistry lessons that carbon, since it has 4 valence electrons, there's those 4 valence electrons. Remember, there's a maximum of 8, right? Let me get that coffee. There's a maximum of 8. So hypothetically, I guess that's one way to put it, there's an empty spot here, 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 and here. So there's essentially, it wants to pair up in some way, shape, or form. Atoms interact and they become more stable when electrons in some way, shape, or form pair up in regions of space. And so what you need to think of is there's a region of space, a region of space, a region of space, and a region of space. So carbon, it has 4 regions of space where it wants to have some sort of pairs of electrons, right? So what we've got to do is just figure out how's that going to look when there's 2 oxygens that want to also try to do the same as well. Well, rule 2 says bond all the atoms, so carbon being at the center. So I'm going to bond carbon to oxygen. Rule 2, done. So now we just have to ask ourselves, where do we go from here? So rule 3 says satisfy the octet rule by adding lone pairs around every atom. So let's just go ahead and do that. So we got 1, 2, 3, 4, 5, 6, right? And then remember right here, that is a pair of electrons. That's a bonding pair, right? This is a lone pair. This right here, bonding pair, right? So if you think about it, there's 2, 4, 6, 8 around the oxygen. Because remember, this is a covalent, that's a covalent bond right there, right? All right, so that has 8 around it. Now if I, let's see, go back. Now there's 2, 4, 6. So that's 2, 4, right? I'm sorry. So let me do that again because I was counting my pairs and writing one at a time so you're not confused. Remember, there's a bonding pattern here, so that's 2, and then there's 4. There's 6, and there's 8. So now carbon has 8 around it. This oxygen already has 2 right here. 4, 6, 8. So now if we were to look at each atom individually, we would see that there's 2, 4, 6, 8 around that oxygen. 2, 4, 6, 8 around that carbon. And 2, 4, 6, 8 around that oxygen. So we have satisfied rule 3. However, now we need to double check here and make sure that all 3 rules are still satisfied. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But we can only have 16 electrons. So we have 4 more electrons than what we need. 4 more electrons, and everything is about a lone pair or a bonding pair. So if there are 4 extra electrons, and that means, if you think about it, we can split this, and we have 2 sets of electrons that have to be in some way, shape, or form redistributed around this in a way that keeps 8 around each atom, but at the same time ensures that we only have 16 electrons according to this example, right? So let me get all this out of the way. And the way that that is done is you have to envision in your mind's eye, electrons are dynamic. So all these electrons, wherever we put bonding pairs or wherever we put dots, the lone pairs, those electrons are constantly moving. I mean, atoms are dynamic. They're not just stuck and frozen like these Bohr models that you learn in earlier chemistry units. I mean, the electrons are constantly moving and shifting in space and around the atom. I mean, your skin, it's fluid, it moves. Everything is fluid. This coffee, bless this coffee, all these molecules are moving constantly. Molecules in your body are moving. The electrons are fluid. They're constantly pushing and pulling on each other. So this Lewis structure, it is representative of a concept, but know that those electrons, like the electron that's right here, those two that are here, at some point in time, they're going to be in this space. At some point in time, they're going to be in that space. They're constantly shifting. But overall, this represents what is happening, generally speaking. Or not generally speaking. It's always keeping this structure to remain as stable as possible. That's a better way to put that. But we have 20 electrons here. So what you have to do is you have to start thinking, if I were to just take a pair of electrons, knowing that they're moving, and I were to move these electrons elsewhere, would there be a way to reshift them so that they are, so like this pair here, it's not between two atoms. This pair, it's not between two atoms. It could shift. This pair, it could shift and move to other atoms. So the question is if we were to do that, if we were to move some electrons between atoms, then they would become a bonding pair because you would have a pair of electrons between two atoms. So with that said, let's think about this. If I erase those and rewrite them so that the electrons are here and here between the two atoms, then all of a sudden we get a bonding pair there. All right, so now I've accounted for one pair of electrons, two of electrons. All right, so now let's think about this for a second. I have 2, 4, 6, 8 electrons that are around that oxygen atom still. Okay? Now, let's do the same over here. Let's just take these. And I could take any one of those lone pairs. It wouldn't matter. I'm just picking those two on the outside just because when they're on the outside, we can think of the two extremes, move things, but we're going to find out that here in a little bit that you're going to be able to recognize from different molecules which electrons you should move because all the patterns repeat themselves. If I were to move these two to right there, then effectively I would get something very similar where I have an electron here in here, which is going to create a bonding pattern right there. And then once again, I can see I have 2, 4, 6, 8 around that oxygen. So now let's count our total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right? We still have too many electrons. Something's not right. Well, let's think about this. Carbon, you learned, has 4 valence electrons. So carbon wants to form 4 bonds. And once it forms those 4 bonds, it has no room for any lone pairs. So if we think about it, this lone pair and that lone pair, they can't stay there anymore. And it makes sense because now there's 2, 4, 6, 8 around that carbon. So this makes sense. Right? So now we have, if we count total, we have 2, 4, 6, 8, 10, 12, 14, 16. We're good to go. All right? Let me erase that. All right? So now we have very much satisfied rule 3. And actually, now that we have all three rules satisfied, this is the Lewis structure for carbon dioxide, with one little minor exception. So let's go back to our molecules, right? So I'm going to use the small model kit that I had. Carbon, remember, is black. And we can see here from our example that the carbon has 4 bonds total. So I'm going to attach 4 bonds to this one carbon atom. Okay, I'm gonna attach to this one carbon atom. And then the carbon is bonded to an oxygen on one side. So I'm going to come over here, put that oxygen, and I'm going to have to bend this just a little bit. And now you can see that we have a carbon to an oxygen. So now I need to put this carbon on the other side. And there it is. So now let's think about this. We have carbon in the center, carbon right here in the center, double bonded to an oxygen. So we could say that this oxygen right here is this right there. And then you can see that right here, there's this post and this post. On this molecule kit, this particular type of kit, the reason why these are very, very important and helpful is the post represents a region of space. And since there's no bond there, what we do is we assume that this post is this lone pair and this post is this lone pair. And now you see how these posts are coming off at these angles. And that's because electrons, since they are all negative, they repel each other. And so what happens is those electrons repel off at these angles. All right? So now we're going to come over here. And then once again, right? Once again, right here. Now I'm going to rotate this so you can oh, you can already see that. But you can see here there's a double bond, carbon double bond to oxygen. I'm going to rotate this. So there's that lone pair and a lone pair. So, but they're still coming off at the same angle. Whether or not I hold it this way or I hold it this way sideways, then those lone pairs are coming off at the same angle. So that would still be, you know, those two and those two right there, right? So once again, we know that there would be a lone pair here and here. All right. So let me get rid of this and I will delete it. Just get that off the screen. We don't need that. So right here, the way I've drawn this, I'm sorry, my apologies, this represents the best Lewis structure for carbon dioxide, okay? So everything pushes out at these angles because if you think about it, go back to what you learned in elementary school. If you were to take the two negative sides of a magnet and bring them close together, they're going to repel. You remember feeling that little force, that force that's there, and you have to kind of actually force it and push it. Well, the electrons, since they're all negative, all these electrons are negative, when they get too close to each other, they repel and they're trying to push away. But you have all these electrons going around the atom, which means that since they're constantly moving, as they get close to each other, they repel. But there may be another electron right here, so then these two repel. So there's this constant movement and repulsion, moving away from each other, of electrons in that region of space around that oxygen, that carbon atom. And that constant movement, it balances out so that this is what, when it stabilizes, you effectively have these 8 around each atom. And so you should then be able, what you need to do is be able to think in your mind's eye, see these electrons, these dots moving around. And if that's the case, then that means that these molecules, they're constantly moving. We'll say these are 2 atoms. And as these 2 atoms become close together and have some sort of chemical bond, like we draw a line and we tend to think that means they're touching. These atoms never touch. So we just draw a line so that we can have the visual concept that right there, that region of space, there's a pair of electrons being shared between those two atoms, but they never touch. Those atoms get really, really close, but they never touch because these negative electrons are trying to repel each other. But remember, there's protons in the nucleus of the atom, and so those positive particles are pulling, the positive particles here are pulling on the negative particles of this atom. And when the negative particles get too close, they want to push each other away. But the positive part of this atom is pulling on the negative part of this atom as well. And so there's this constant pushing and pulling back and forth between these atoms. So if you think about it, every atom in your body, every atom in the universe, it's pulsating. It's moving back and forth constantly. It's in constant motion. I don't care if we're looking at this tabletop. The atoms there, they're moving back and forth. They're just very tightly packed together. And so we feel what we say is that physical property, hardness, right? Hardness right here. Whereas the molecules in this coffee, placid coffee, they're further apart, so they're flowing around each other, but they're still pulsating, moving back and forth according to their Lewis structure, okay? And there's a Lewis structure for everything. Every single molecule you can think of has 3 dimensions. We live in a 3-dimensional world. Lewis structures are our way to try to put a 3-dimensional concept in a 2-dimensional form. But these model kits, these right here, what they do is they literally model what we know is happening in the universe, and they put 3 dimensions to what our 2-dimensional paper can represent. So instead of having to be a really good artist, all you have to do is be able to do what's right there on paper and draw a Lewis structure with a few minor adjustments, like knowing that you have to draw those lone pairs coming out at angles, right? And then these model kits are our way of being able to take that and represent it. And notice I'm having to put some force into bending this molecule, right? It's a fairly new set, so these are... But you can see that it's that same shape and pattern that was here. Okay, we build these kits. Now, to do that, to represent that. Now, what you have to remember is this, is that there's still lone pairs here. These kits don't have it, and this is the standard way to do it. These kits just happen to, this is an older set. They're really hard to find. I happen to have a few of these, so I love to use these for training purposes. This is a standard kit. This is sometimes referred to as like a ball and stick model, right? Because, you know, the sticks represent the bonds, and then right here the ball part just represents the atom. And the different color, different atom type. Okay, so there you go. There's 2 atoms. In the next lesson, we will take a look at Lewis structures, but with ions, and ask ourselves what happens when we have an ion. Come stick around and or take a look at the next video. I'll be uploading that. It's always good to see you. It's always great learning with you. Stay curious. I will see you in class, or I'll hear from you virtually for some questions. Take care. Hope this helped. Bye.